On October 29th, 2025, something impossible happened. A wanderer from another star, 3I-ATLAS, passed near our Sun and exploded. Not with fire or dust, but with a brilliant blue light that shouldn't exist. No dust, no fragments, just water vapour pouring out at impossible rates. And when the James Webb Space Telescope looked closer, it found something haunting. A 50-foot deep shell of irradiated crust, as if time itself had sealed it shut. Billions of years of exposure. And then, this. Something changed inside that shell when sunlight hit it. And the question isn't what caused the explosion. It is why an object designed to survive eternity awoke violently near our star. Stay until the end, because tonight you'll understand why 3I-ATLAS may be the first interstellar object that fought back. If this mystery has you hooked the way it has me, make sure to like and subscribe so you don't miss what's coming next. Tell me where you're watching from, and share this video anywhere you want to keep the conversation alive. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. The outburst nobody saw coming. On October 29th, 2025, something happened in the darkness between worlds that nobody predicted. An object from beyond our solar system, travelling faster than a bullet, suddenly exploded with light. Not the gentle brightening astronomers expected from a comet warming in the sun's embrace, but a violent, unexpected surge that lit up telescopes across Earth like a cosmic alarm bell nobody knew how to silence. The object is called 3I-ATLAS, and on that October morning it reached Perihelion, the closest point in its path to our Sun. Perihelion for a comet is supposed to be predictable. The sun's heat warms the ice, gas vents into space, the object brightens gradually, like turning up a dimmer switch. Astronomers have watched this dance for centuries. They know the steps, they know the rhythm. But 3I-ATLAS didn't follow the choreography. Instead, it detonated with brightness in the days leading up to its closest approach, as if something fundamental about it had been triggered, activated, or broken free. Let me give you the numbers so you understand the scale we're dealing with. 3I-ATLAS approached the Sun to a distance of about 1.4 astronomical units, roughly 130 million miles, or 210 million kilometres. That's actually farther from the Sun than Earth is, which makes the outburst even more bizarre. Most comets need to get much closer before they start behaving dramatically. Yet here was this visitor from another star system, still relatively distant, flaring up like it had crossed some invisible threshold. And the speed, this thing is moving at approximately 130,000 miles per hour. That's about 210,000 kilometres per hour, or roughly 60 kilometres per second if you prefer the scientific notation. It's travelling on what astronomers call a hyperbolic trajectory, which is the mathematical way of saying it's not bound to our Sun. It came from somewhere else, and it's leaving, never to return. The trajectory's eccentricity is around 6.2 for context. Anything above 1 means the object is unbound. This isn't a comet that belongs to us. It's a stranger passing through. But speed and trajectory alone don't make 3I-ATLAS remarkable. What makes it unforgettable is how it looks and behaves. When astronomers turned their spectrographs toward this brightening interloper, they saw something that made them check their instruments twice. The light coming from 3I-ATLAS was blue. Not the warm, dusty yellow-white of a typical comet, but blue, bluer than the Sun itself. That blue glow tells a story about molecules that shouldn't be there in those quantities. Early spectroscopic analyses detected diatomic carbon, written as C2 in chemistry notation, and amidogen, NH2. These are molecular fragments that form under specific conditions, and their presence in such abundance suggests the object's composition, or the way it's releasing material, is fundamentally different from the comets we know. Then there's the dust-tail paradox, and this is where things get truly strange. Every comet you've ever seen in a photograph, Halley's Comet, Hale-Bopp Neowise, has a tail, usually two actually, a blue ion tail blown back by the solar wind, and a white or yellow dust tail pushed by radiation pressure. The dust tail is the signature move of a comet. It's what makes them look like cosmic paintbrushes streaking across the sky. Conventional wisdom says that as a comet heats up near the Sun, its ice sublimates, releasing trapped dust particles that get swept into a long, graceful arc pointing away from the Sun. 3I-ATLAS, in those early observations before Perihelion, didn't have one. Or if it did, the dust tail was so weak, so anemic, that it barely registered. Observers scanning the sky saw an object brightening dramatically, but leaving no obvious trail of debris behind it. It was like watching someone sprint across a beach and leave no footprints. Astronomers started asking uncomfortable questions. Where's the dust? Is this thing actually a comet? Or is it something else wearing a comet's disguise? Later observations would show a tail did eventually appear, but even that raises more questions than it answers. Why the delay? Why did the dust take so long to show up? Normal comets don't wait. They start shedding material as soon as solar heating reaches them. The missing tail, or the delayed tail, became one of the defining mysteries of 3I-ATLAS, a clue that something about its structure or composition doesn't fit the standard model. And make no mistake, this violates the baseline models. Astronomers have centuries of comet observations. They have mathematical models that predict brightness curves, outgassing rates, dust production, all calibrated against dozens of well-studied comets. 3I-ATLAS broke those models like they were made of glass. The rapid brightening, the blue emission, the absent or delayed dust tail, these aren't minor deviations. These are red flags suggesting that our understanding of how comets work might be incomplete, or worse, wrong. So we're left with a mystery that cuts to the core of planetary science. Is 3I-ATLAS just a weird comet, an outlier, a statistical anomaly, but still fundamentally a frozen chunk of ice and rock? Or is it something else entirely? Something that requires us to expand our definitions, revise our theories, maybe even question what we think we know about objects wandering between the stars. The stakes here are higher than you might think. If this is just another comet, then fine, we update our models, add a footnote, move on. But if it's not, if 3I-ATLAS represents a new class of object or behaves according to rules we haven't discovered yet, then the implications ripple outward. It means the interstellar medium might be filled with objects we don't understand. It means our assumptions about how small bodies form, survive, and evolve during journeys between stars could be fundamentally flawed. It opens doors to new physics, new chemistry, new questions about planetary formation, and the life cycle of matter in the galaxy. And here's the question that should keep you awake at night. What if this cosmic visitor isn't only from another star system? What if it's been changed, transformed, or even engineered? What if the object we're seeing isn't what left its home system billions of years ago, but something that's been shaped by forces we're only beginning to understand? That question is what drives everything that follows. Because before we can answer it, we need to look beneath the surface, literally, and understand what billions of years in the void between stars can do to an object. We need to understand the mask before we can see the face underneath. Part 2, Peek Beneath the Crust, JWST, cosmic rays, and a 50 to 65 foot shell. When the James Webb Space Telescope turned its infrared eye toward 3I-ATLAS, it wasn't looking for a comet. It was looking for a crime scene, or maybe an archaeological site. The difference between those two descriptions might be the difference between natural processes and something else entirely. But either way, what JWST found was a surface that had been profoundly, irreversibly altered. The James Webb Space Telescope, along with ground-based spectrographs scattered across Earth, began piecing together a picture of 3I-ATLAS's outer layer. What they discovered was an unusually thick crust of radiation-processed material covering the object like armour. This isn't a thin patina of space weathering like you'd find on an asteroid in our solar system. This is a shell approximately 15 to 20 metres thick. That's roughly 50 to 65 feet if you're measuring in human terms. To put that in perspective, it's about the height of a 5-story building. Imagine an entire 5-story building's worth of material that's been chemically and physically transformed by exposure to the harshest environment in the universe. The mechanism behind this transformation is cosmic ray bombardment, and you need to understand what that means in practical terms. Our solar system exists inside a protective bubble called the heliosphere, a region of space dominated by the solar wind, charged particles streaming out from the sun that push back against the interstellar medium. The heliosphere acts like a shield, deflecting most galactic cosmic rays and reducing radiation exposure for everything inside it. Earth's magnetic field adds another layer of protection. We live in a relatively safe neighbourhood, cosmically speaking. But 3I-ATLAS spent billions of years outside any heliosphere, drifting through interstellar space with no protection whatsoever. Out there, It was exposed to the full fury of galactic cosmic rays, high-energy protons, heavy atomic nuclei, electrons accelerated to nearly the speed of light by supernovae and other violent cosmic events. These particles don't just hit the surface and bounce off, they penetrate deep into the material, smashing into molecules, breaking chemical bonds, rearranging atoms, creating new compounds that never existed when the object first formed. Over millions and billions of years, this bombardment processes the outer layers of the object, turning pristine ice and rock into something fundamentally different. Computer simulations of this process suggest that for an object like 3I-ATLAS, travelling through interstellar space for potentially billions of years, the radiation-processed layer could reach depths of 15 to 20 metres. That's not speculation pulled from thin air, it's based on models of particle interaction, measured cosmic ray fluxes in interstellar space, and experiments where scientists expose ice and rock samples to simulated cosmic radiation in laboratories. The implications of this are profound and unsettling. If the surface of 3I-ATLAS is a 50 to 65 foot thick shell of transformed material, then what we're seeing, what our spectrographs are measuring, what our telescopes are photographing, is not the original object. It's a mask, a facade created by billions of years of particle bombardment. The true composition of 3I-ATLAS, the material it carried from its birth system, might be buried beneath this processed crust, hidden and protected like a secret waiting to be revealed. This completely upends one of the foundational assumptions about interstellar objects. Astronomers get excited about visitors from other star systems because they're supposed to be pristine samples, time capsules carrying information about planetary formation in alien solar systems, uncontaminated by the processes that shaped our own neighbourhood. But if the surface has been so thoroughly processed, then the data we collect might tell us more about interstellar radiation than about the object's origins. It's like trying to read a book where the first 50 pages have been overwritten with static. Some of the observational evidence supports this crust hypothesis in unexpected ways. Researchers analysing spectroscopic data from 3I-ATLAS have reported anomalies in metal abundances, specifically unusual ratios of nickel to iron. In typical solar system bodies, iron dominates over nickel by predictable amounts. That ratio is one of the fingerprints we use to classify and understand small bodies. But 3I-ATLAS shows nickel signatures that are stronger than expected, a pattern that some scientists, including Avi Loeb from Harvard, have flagged as worthy of closer investigation. Now, there are natural explanations for unusual metal ratios. Different formation environments, different temperatures, different chemical pathways during planetary system formation could all produce non-standard compositions. But there's another possibility that the radiation crust model offers. What if the surface processing preferentially affects certain elements, creating false signatures that don't reflect the original composition? What if the nickel we're detecting is a byproduct of cosmic ray spallation reactions, where heavy nuclei get broken apart into lighter fragments? Or what if the crust is selectively releasing certain metals while trapping others? The practical consequence is this. If we want to understand what 3I-ATLAS really is, where it came from, what its birth environment was like, we need to get past that crust. We need the solar heating to erode away the processed layers and expose the pristine interior, if there is a pristine interior. That might happen as 3I-ATLAS continues to warm and shed material, or it might not. The crust could be stable enough to survive perihelion intact, in which case the true object remains hidden, perhaps forever, unless the object breaks apart or undergoes some catastrophic event that cracks the shell. This is where the story takes a speculative turn, and I want you to consider this carefully because it matters. What if the radiation crust isn't just a passive byproduct of interstellar travel? What if, through some combination of chemistry and physics we don't fully understand, that processed layer serves a function? Could it act as insulation, protecting the interior from further degradation? Could it regulate the release of volatiles, controlling how and when the object sheds material? Could it, and I'm going to say this even though it sounds like science fiction, could it have been designed to do these things? That last question is going to sound absurd to many scientists, and maybe it should. We don't invoke artificial explanations without extraordinary evidence, and we don't have that evidence yet. But here's the thing. We also don't fully understand what billions of years of cosmic ray bombardment can do to complex organic chemistry, ice mixtures, and mineral assemblages. We don't know if there are self-organizing processes that could create structure, and function from chaos. Nature is capable of extraordinary things that look designed but aren't. Evolution is proof of that. So when we look at this 50 to 65 foot shell and see anomalies, we have to stay open to multiple explanations, even uncomfortable ones. The viewer hook here isn't about jumping to conclusions. It's about recognizing that you think you're seeing an object from another star system, but maybe you're not seeing the real thing. You're seeing the altered mask, the transformed exterior, the shell that formed during an inconceivably long journey through the dark. The question of what lies beneath, and whether we'll ever get to see it, is one of the central mysteries of 3I-ATLAS. And as we're about to discover, that hidden interior might hold the key to understanding why this object breaks every rule we thought we knew about comets. Part 3. Composition, Trajectory and Size. Why this object keeps breaking the rules. The more data astronomers collect on 3I-ATLAS, the less it resembles anything we've seen before. It's not just one anomaly or one unexpected measurement. It's a constellation of oddities that, when taken together, paint a picture of an object that refuses to fit into any comfortable category. Let's start with what should be the simple part. What is this thing made of? Spectroscopic observations have revealed a composition that's both familiar and strange. 3I-ATLAS shows strong signatures of carbon monoxide and carbon dioxide, CO and CO2 in chemistry shorthand. These are common enough in comets, so no surprise there, but the ratios are off. The amount of CO relative to CO2 is higher than what we typically see in solar system comets, suggesting either a different formation temperature, a different chemical environment during birth, or selective processing of one molecule versus the other during the interstellar journey. Then there's the water. 3I-ATLAS is outgassing water vapour at rates that have surprised observers. Water is the most common volatile in comets. It's what makes up most of the ice in these dirty snowballs. But the rate at which 3I-ATLAS is releasing water doesn't match the models based on its distance from the Sun and its estimated size. It's producing too much, too fast, as if there's a reservoir of water ice closer to the surface or more easily accessible than conventional comet structure would predict. Remember that 50 to 65 foot radiation crust we talked about? Maybe the crust is cracking, creating vents that allow water vapour to escape in concentrated jets rather than diffuse sublimation. And then there are the metals. Multiple research teams have reported detecting nickel in the spectrum of 3I-ATLAS, and not just trace amounts, enough to be noteworthy. More specifically, they're seeing nickel in abundances that exceed iron, which is backwards from what we expect. In our solar system, in meteorites, in asteroids, in everything we've measured, iron dominates over nickel by factors of 10 or more. But 3I-ATLAS seems to violate that rule. Some researchers have proposed that this could be a signature of a different stellar environment, where supernova nucleosynthesis produced unusual element ratios. Others, including Avi Loeb, have suggested it might indicate something more exotic, perhaps even artificial materials, though that's at the far speculative end of the possibilities. Now let's talk about size and mass, because this is where 3I-ATLAS really starts to look like an outlier. Mass estimates for the object put it at over 33 billion tons. To give you a comparison, Halley's Comet, probably the most famous comet in human history, has an estimated mass of about 22 billion tons. So 3I-ATLAS is roughly 50% more massive than Halley. And remember, Halley is bound to our solar system, orbiting the Sun every 75 or 76 years. For an interstellar comet, for something that wandered in from another star system, 33 billion tons is anomalously large. Why does that matter? Because the process of ejecting an object from a planetary system is violent and chaotic. Gravitational interactions with giant planets can fling smaller bodies out into interstellar space, but the bigger and more massive an object is, the harder it is to eject. It takes more energy, more precise orbital geometry, more luck. The fact that 3I-ATLAS is so massive suggests either it came from a system with particularly violent dynamics, or it represents a rare statistical outcome, or, and this is the uncomfortable possibility, it's not a naturally ejected comet at all, but something that was placed on its trajectory deliberately. The trajectory itself adds more fuel to this fire of confusion. 3I-ATLAS is on a hyperbolic orbit with an eccentricity of approximately 6.2. That's extremely hyperbolic. It means the object is moving way faster than escape velocity from the Sun, is not even close to being captured, and its velocity is about 60 kilometers per second, which is fast even for interstellar objects. Most stars in our galactic neighbourhood move at speeds of 20 to 30 kilometers per second relative to each other. 3I-ATLAS is hauling through space at twice that speed, which raises questions about where it came from and what might have accelerated it. There's another curious detail about the trajectory that some researchers have pointed out. The orbital inclination relative to the ecliptic, the plane where Earth and most planets orbit, is relatively low. For a truly random interstellar visitor, you'd expect the inclination to be, well, random. Objects should be coming in from all angles, all directions, because space is three-dimensional and isotropic. But 3I-ATLAS's path is somewhat aligned with the ecliptic. Not perfectly, but more than pure chance might suggest. This could mean nothing, statistics are funny, and sometimes coincidences happen. Or it could mean the object's trajectory was influenced by something we haven't accounted for. Some gravitational interaction or prior encounter that shepherded it into a plane more aligned with our solar system's architecture. When you combine the composition anomalies, the mass problem, the trajectory questions, and that radiation-processed crust hiding, who knows what underneath, you start to see a pattern. Each individual piece might have a natural explanation, but taken together, they form a picture of an object that doesn't quite fit the standard model of what an interstellar comet should be. It's like finding a puzzle piece that's almost the right shape but not quite. You can force it into place, but it doesn't sit flush with the others. This is where controversy enters the conversation. The mainstream scientific position is cautious. Yes, 3I-ATLAS is unusual. Yes, it challenges our models, but we've only studied 3 interstellar objects so far. Oumuamua in 2017, Borisov in 2019, and now 3I-ATLAS. 3 data points is not a large sample. We can't generalize from 3 examples. So maybe the problem isn't with 3I-ATLAS. Maybe the problem is that our models are based on a biased sample of objects that stayed in our solar system, and the interstellar population is just more diverse than we realized. That's a reasonable position. But there's another camp, smaller but vocal, that argues we shouldn't close the door on alternative explanations prematurely. Avi Loeb, who chairs Harvard's astronomy department and has made a career of asking uncomfortable questions, has suggested that the anomalies surrounding 3I-ATLAS, just like those surrounding Oumuamua before it, warrant serious consideration of artificial origins. Not aliens necessarily, but artifacts, probes, spacecraft, structures built by intelligence and sent wandering through the galaxy for purposes we can only guess at. This is not a popular hypothesis in the astronomical community. Most scientists recoil from invoking intelligence because it violates Occam's razor, the principle that simpler explanations are more likely to be correct. A comet is simpler than a spacecraft. Natural processes are simpler than engineering. But Loeb's counter-argument is that Occam's razor only applies when all explanations fit the data equally well. When natural explanations require increasingly tortured logic, increasingly specific conditions, increasingly unlikely coincidences, maybe it's time to at least consider that the data is pointing somewhere uncomfortable. Let's compare 3I-ATLAS to the previous interstellar visitors for context. Oumuamua was the first confirmed interstellar object detected in our solar system, and it was bizarre from the start. Elongated, tumbling, no visible outgassing but exhibiting non-gravitational acceleration, as if something was pushing it. Astronomers eventually settled on a model involving outgassing of hydrogen ice, though not everyone is convinced. 2I Borisov was much more comet-like, much more normal, which relieved a lot of scientists because it suggested Oumuamua might have been a one-off anomaly. But now 3I-ATLAS arrives, and it's anomalous again in completely different ways. Massive, rapid brightening, radiation crust, metal anomalies, delayed dust tail. If Oumuamua was strange and Borisov was normal, then 3I-ATLAS is strange in a new direction, which raises the question, how common is strange? And at what point do we stop calling things anomalies and start calling them a pattern? The hidden angle in all of this is that the composition and trajectory oddities are not independent. They're connected by the radiation crust model. If the surface is processed and transformed, then our spectroscopic measurements might be misleading. If the mass is higher than expected because the interior is denser, or more compact than typical cometary material, that affects how we interpret the trajectory. Maybe the object experienced more drag or more radiation pressure than we're calculating, which would make the trajectory look weirder than it actually is. everything feeds into everything else, creating a web of interconnected mysteries where pulling on one thread just tightens the knots elsewhere. If composition and trajectory are already pushing the boundaries of conventional understanding, then the dust tail mystery is where those boundaries start to collapse entirely, because the absence or delay of a proper dust tail doesn't just challenge our models of comets, it challenges our understanding of what a comet even is. Part 4. Dust tail mystery and what it means for the nucleus. Imagine you're watching a campfire and someone throws a log onto the flames. You expect smoke, sparks, maybe a burst of embers spiralling into the night sky. Now imagine instead the log just glows brighter and hotter, but produces no smoke, no sparks, no visible ash. You'd probably check to make sure it was actually a log, and not something else disguised as wood. That's essentially what astronomers experienced when they watched 3I-ATLAS approach perihelion. Conventional comets nearing the Sun are supposed to generate visible dust tails. The mechanism is straightforward. Solar heating causes ice on the surface, and near-surface layers to sublimate, transitioning directly from solid to gas. That gas carries with it embedded dust particles, silicates, organics, tiny grains that were frozen into the ice when the comet formed. Once liberated, these dust particles are pushed away from the comet by radiation pressure, the physical momentum of sunlight, creating a broad, curved tail that points generally away from the Sun, but lags behind the comet's motion, because dust particles have mass and inertia. This process should begin well before perihelion and continue well after. The closer to the Sun, the more intense the heating, the more vigorous the outgassing, the more dramatic the dust tail becomes. It's predictable. It's one of the fundamental signatures of cometary behaviour. Except 3I-ATLAS, in those crucial observations before October 29th, wasn't producing one, or at least not a strong one. Observers reported seeing the blue coma, detecting gas emission, measuring brightening, but the dust tail was weak or absent. Let me be clear, a tail did eventually appear. Later observations from facilities like the TD Observatory captured imagery showing material being ejected from the nucleus. But the timing was wrong, the morphology was strange, and the whole sequence didn't follow the script. That delay, that reluctance of the dust to show up, is at the heart of one of 3I-ATLAS's deepest mysteries. There are two main hypotheses to explain this, and they paint very different pictures of what the nucleus might be like. Hypothesis A suggests that 3I-ATLAS is extremely ice-rich and dust-poor. Maybe during its formation, it accreted in an environment where dust grains were scarce or were preferentially lost. Maybe subsequent processing during its interstellar journey somehow concentrated the ice and depleted the dust. If the object is essentially a giant dirty iceberg with very little solid debris embedded in it, then when it heats up it produces mostly gas and very little dust. The tail would be primarily an ion tail, the blue glow from ionized gases with minimal dust contamination. This hypothesis has some appeal because it's simple and natural. Comets form in cold, distant regions of planetary systems where conditions vary widely. Some regions might produce ice-rich, dust-poor bodies. But it's also unsatisfying because it doesn't explain the delay. Even a dust-poor comet should produce whatever dust it has relatively quickly once heating begins. The reluctance of 3I-ATLAS to show a visible tail suggests something more complicated is going on. That brings us to hypothesis B. The dust is there, but it's trapped or delayed by structural factors. One possibility is geometry. If the dust tail is pointing toward or away from Earth, we might not see it clearly due to foreshortening. But multiple observatories at different locations should have caught at least some viewing angle where the tail became visible and the delay persisted across multiple observing runs. A more interesting possibility involves the radiation crust and a phenomenon called the CO2 cooling shield effect. Here's how that works. Carbon dioxide ice sublimates at lower temperatures than water ice. So as 3I-ATLAS approaches the Sun, CO2 starts venting first, before water ice gets warm enough to sublimate significantly. The sublimating CO2 absorbs heat. Phase transitions are endothermic, meaning they suck energy out of the surrounding material, which actually cools the surface and delays the onset of water ice sublimation. This creates a protective layer, a coolant effect that keeps the nucleus surface below the threshold temperature for major water outgassing until the object gets much closer to the Sun. Only when solar heating overwhelms the cooling from CO2 sublimation does the water ice begin to sublimate in earnest. And water ice is where most of the embedded dust lives. So you get a delay between the CO2-driven brightening and the dust-driven tail formation. Add to this the 50 to 65 foot radiation crust, and you have a compounding effect. If the crust is tough, compact, and relatively impermeable, it could trap dust beneath it, even as gases percolate through cracks and pores. The gases can escape relatively easily. Molecules are small, they diffuse, they find pathways. But dust grains are much larger and can't escape until the crust physically breaks down, cracks, or erodes away. So you'd see gas emission first, followed much later by dust emission once the structural integrity of the crust fails. This model predicts that the dust tail should appear suddenly, almost catastrophically, once the critical threshold is crossed. And indeed, later observations of 3I-ATLAS showed dramatic jets and plumes oriented toward the sun, sunward jets, which are unusual because radiation pressure should push material away, not toward the sun. These jets suggest localized breakthroughs, where pressurized gas and dust finally punched through the crust and erupted in concentrated streams rather than diffuse sublimation. The consequences of these hypotheses for the structure of the nucleus are profound. If hypothesis A is correct and the nucleus is truly dust poor, then 3I-ATLAS is not a typical comet. It's more like a cosmic iceberg, a chunk of relatively pure volatiles with minimal rocky or metallic contamination. That raises questions about how and where it formed. What kind of planetary system environment produces such clean ice? If hypothesis B is correct and the dust is trapped beneath a protective layer, then the nucleus might be more like a rock or metal core surrounded by ice pockets and capped with that thick radiation crust. The interior structure could be heterogeneous, layered, with volatile-rich regions and volatile-poor regions creating complex outgassing behavior. This is less like a comet and more like a hybrid object, part comet, part asteroid, with properties of both. There's also a third possibility that nobody wants to say out loud, but that lingers in the subtext of scientific papers. What if the dust tail is minimal because the object isn't primarily a comet nucleus at all? What if it's a manufactured structure with an ice coating? What if the radiation crust isn't natural weathering but engineered shielding? I know how that sounds. I know it triggers immediate skepticism, and rightly so, but if we're being intellectually honest, we have to admit that some of the observations, the metal anomalies, the trajectory questions, the delayed dust release, the structure implied by the data are at least consistent with that interpretation, even if they don't require it. The visual metaphor here is the difference between a freshly made snowball and one that's been sitting outside all winter, accumulating layers of ice, dirt, and compacted snow. The fresh snowball is uniform, predictable. You know what you're getting when you pick it up. The weathered one is layered, complex, potentially deceptive. The surface doesn't tell you what's inside. 3I-ATLAS is the weathered snowball, and we're trying to figure out if the core is more snow or something else entirely. Observational evidence from facilities like Tidy Observatory captured what they described as a giant jet oriented toward the sun, visible in early November 2025. That's exactly the kind of catastrophic breakthrough you'd expect if pressurized volatiles beneath a crust finally found an escape route. It's also the kind of behavior that's hard to model with standard comet physics. Sunward jets require specific geometries, specific thermal distributions, specific structural properties that aren't typical. The dust tail mystery ties directly back to the transformed relic hypothesis we discussed earlier. If the radiation crust dominates the surface properties, if the interior is hidden and structurally complex, then the absence or delay of the dust tail makes sense. It's a symptom of the deeper condition, an object that's been profoundly altered by its journey, wearing armour that hides its true nature until that armour breaks. And that brings us to the larger questions, the ones that make this story bigger than just one weird comet. What if objects like 3I-ATLAS aren't rare? What if interstellar space is filled with transformed relics, dirty snowballs wrapped in radiation armour, wandering between stars and occasionally passing through solar systems like ours? What if some of them, a small fraction, aren't natural at all? What if they're probes, seeds, messages, or artifacts left by civilizations we haven't met yet? These questions might sound like science fiction, but they're being asked by serious scientists publishing in peer-reviewed journals. And the reason they're being asked is because the data keeps refusing to cooperate with comfortable, simple explanations. Part 5. Planetary Seeds and Artificial Origins, the Bigger Questions. Let's zoom out for a moment and ask a question that sounds almost philosophical, but has very concrete scientific implications. What if some interstellar objects aren't just frozen comets, but carry deeper significance? What if they play roles in cosmic ecology that we're only beginning to understand, or worse, haven't imagined yet? There's a hypothesis in planetary formation theory that's been gaining traction over the past few years, and it addresses one of the classic unsolved problems in the field. The problem is called the meter-size barrier, and it goes like this. When a planetary system is forming, you start with a disk of gas and dust around a young star. Tiny dust grains stick together through electrostatic forces and gentle collisions, gradually growing into pebbles, then rocks, then boulders. But when you get to objects about a meter across, something breaks down. At that size, collisions between objects are energetic enough to shatter them rather than fuse them together. You're also in a size range where aerodynamic drag from the gas disk causes rapid orbital decay. Meter-size objects spiral into the star and get destroyed before they can grow larger. This is a real problem because planets exist, which means something must bridge that gap between meter-size rubble and kilometre size. Planetesimals that have enough gravity to continue growing through accretion. There are various proposed solutions: turbulence in the disk, pressure traps, streaming instabilities, but none of them work perfectly in all scenarios. Now here's where it gets interesting. What if the solution doesn't have to happen in every planetary system? What if large objects can be imported? Researchers like Suzanne Falsner and others have proposed that interstellar objects, preformed bodies drifting through the galaxy, could be captured by young planetary systems and act as accretion seeds. If a 10-kilometre wide object wanders into a protoplanetary disk and gets gravitationally captured, it's already past the meter-size barrier. It can start accreting material immediately, building up mass through collisions with the abundant pebbles and boulders in the disk. Over time, this imported seed could grow into a full-fledged planet, or at least a large moon or dwarf planet. This hypothesis solves multiple problems at once. It explains how you bypass the meter-size barrier in systems where local growth mechanisms struggle. It predicts that some planets in the galaxy should have unusual compositions because they started from imported material rather than locally formed material. And it suggests that interstellar objects might be far more important to planetary system architecture than we've previously considered. They're not just cosmic debris, they're building blocks. Now apply this framework to 3I-ATLAS. Could it be one of these planetary seeds that never got captured? A wandering accretion core that spent billions of years drifting through interstellar space, accumulating that radiation crust, never finding a home? If so, its size, mass, and composition anomalies start to make more sense. It's not a typical comet because it was never meant to be a comet. It's a failed planet or a planetary embryo, or the core of what might have become a terrestrial world if it had landed in a protoplanetary disk instead of sailing past into the void. This interpretation is speculative but scientifically grounded. It doesn't require new physics or exotic materials, just a recognition that the interstellar population might be more diverse and more functionally important than we've assumed. It also opens fascinating questions about panspermia, the hypothesis that life, or at least the chemical precursors to life, can be transported between star systems on objects like this. If 3I-ATLAS is a planetary seed carrying organic molecules, water and complex chemistry from another stellar system, and if it had been captured by a young star 4.5 billion years ago, could it have seeded a planet with the ingredients for life? Could Earth itself have started from an imported core? These are not fringe ideas. They're being discussed in mainstream planetary science because the data from objects like 3I-ATLAS forces us to think bigger. But there's another interpretation that's more controversial, more uncomfortable, and yet refuses to go away no matter how many scientists roll their eyes at it. The possibility of artificial origin. Avi Loeb has been the most prominent voice arguing that we must keep this possibility on the table. His position is not that 3I-ATLAS is definitely artificial. He's very clear about that. But that the scientific method requires us to consider all hypotheses consistent with the data, not just the ones that make us comfortable. When you have an object with unusual metal ratios, a trajectory that's somewhat aligned with the ecliptic, a mass larger than expected, behaviour that violates standard Comet models, and a structure that might include a thick processed shell, you have to ask, could this be an artifact? What would an interstellar probe even look like? We have exactly one data point, the spacecraft we've built ourselves. Voyager 1 and Voyager 2, Pioneer 10 and 11, New Horizons, these are our probes, launched decades ago, now in or approaching interstellar space. They're small, a few hundred kilograms, designed for specific scientific missions. But imagine a civilization with resources and timescales we can't comprehend. Imagine they want to send something durable, something that can survive millions or billions of years travelling between stars. You wouldn't build it like Voyager. You'd probably encase it in shielding, maybe ice, which is abundant and effective at stopping radiation. You'd make it massive enough to survive collisions with interstellar debris. You'd give it a trajectory that maximises encounters with planetary systems. From the outside, such a probe might look exactly like a comet. The ice shielding would sublimate as it approached a star, creating outgassing that mimics cometary behaviour. The radiation crust would form naturally during the journey, providing additional protection. The only way to tell the difference would be through detailed analysis of composition, structure and behaviour, exactly the kind of analysis that keeps producing anomalies when applied to 3I-ATLAS. Now, I want to be very clear about something. There is no smoking gun here. There is no single measurement that proves artificial origin. What there is a pattern of oddities that resists simple natural explanations and that, if you squint at it from the right angle, looks like it might be consistent with intelligent design. That's not proof, it's not even strong evidence. But it's enough to justify asking the question. The implications of each scenario, natural seed versus artificial origin, are profound and different. If 3I-ATLAS is a natural planetary seed, then the implications ripple through our understanding of how planetary systems form. It means the galaxy is full of wandering building blocks, cosmic Lego bricks that occasionally get incorporated into new worlds. It means planet formation is more stochastic, more dependent on chance, encounters, more influenced by the galactic environment than we thought. It raises the odds that life's ingredients are widely distributed, that the chemistry of Earth might have roots in multiple star systems, that we're more cosmically connected than our provincial position in the galaxy would suggest. If 3I-ATLAS is artificial, the implications are even more staggering. It means we're not alone, or at least we weren't alone at some point in the galaxy's history. It means intelligence capable of interstellar engineering has existed or exists. It means there might be networks of probes, fleets of spacecraft, archaeological remnants scattered through the galaxy waiting to be discovered. It changes the odds for SETI, the search for extraterrestrial intelligence, because it suggests that civilizations build things that last, that travel, that leave traces. It also raises uncomfortable questions. Why send probes? What are they looking for? Are they still active, reporting back to creators who might be long extinct? Or are they dead relics, silent monuments to vanished civilizations? The scientific community's attitude toward these questions is mixed, and that's putting it mildly. The mainstream position is deeply skeptical of artificial origin claims. Skepticism is healthy. It's the immune system of science, protecting against wishful thinking and pattern matching gone wrong. But some scientists argue that skepticism has become reflexive dismissal, that the stigma around alien hypotheses is so strong that researchers avoid even investigating certain possibilities for fear of damaging their careers. Avilobe has been outspoken about this, arguing that the scientific method doesn't care about your comfort level. If a hypothesis is testable and consistent with observations, you investigate it. You don't preemptively rule it out because it makes you uncomfortable, or because your colleagues might mock you. He's called for NASA and other space agencies to release all the data they've collected on 3I-ATLAS, spectroscopy, photometry, trajectory measurements, everything, so that independent researchers can analyse it without institutional filters or biases. That call for transparency is important, because it gets at a deeper issue in modern astronomy. We have more data than ever before, but much of it is locked behind institutional access, proprietary instruments, or simply hasn't been processed and published yet. If 3I-ATLAS really is as anomalous as it appears, then the scientific community needs full access to the raw data to figure out what's going on. Transparency isn't about proving aliens exist, it's about proving they don't. if that's what the data shows. Either way, we need to see everything. There's a historical parallel worth mentioning. Oumuamua. When that object was discovered in 2017, it exhibited anomalies, the elongated shape, the tumbling rotation, the non-gravitational acceleration that some researchers interpreted as potentially artificial. Loeb proposed that it could be a light sail, a thin reflective structure pushed by radiation pressure, which would explain the acceleration without requiring outgassing. The mainstream community countered with natural explanations, hydrogen ice outgassing being the most widely accepted, but the debate highlighted how little we actually know about interstellar objects, and how quickly we default to comfortable explanations even when they require increasingly specific conditions. 2I Borisov was different. It looked like a normal comet, behaved like a normal comet, fit the models. That should have settled the question. Interstellar objects are just comets and asteroids, nothing special. But now 3I-ATLAS arrives, and it's anomalous again in completely different ways. If 1 out of 3 interstellar objects we've studied is weird, that's an anomaly. If 2 out of 3 are weird in different ways, that's starting to look like a pattern, and patterns demand explanations. The critical thinking angle here is that we shouldn't jump to aliens, but we also shouldn't dismiss oddness just because it's uncomfortable. Science advances by taking anomalies seriously, not by explaining them away. Every major revolution in physics and astronomy, heliocentrism, relativity, quantum mechanics, dark matter, started with observations that didn't fit the prevailing models. The scientists who made those breakthroughs were the ones willing to say, I know this sounds crazy, but what if the models are wrong? That's where we are with 3I-ATLAS. The models say it should behave one way, but it behaves another. The models say its composition should look one way, but it looks another. The models say its dust tail should appear at a certain time, but it doesn't. At some point, you have to ask whether the problem is with this one object or with the models themselves. And if the models are incomplete, what are they missing? Natural processes we haven't discovered, chemistry we don't understand, or something else? Something that requires us to expand our definitions of what counts as a natural object. As 3I-ATLAS moves away from the Sun in the coming months, we'll have a chance to watch what it does next. Will it fade predictably, following the inverse square law of solar illumination? Will it continue to outgas, producing jets and plumes as its crust breaks down? Will we detect any additional trajectory anomalies, tiny deviations from a purely ballistic path that might indicate internal structure or active processes? These are the questions that should keep astronomers glued to their telescopes through the winter of 2025 and into 2026. Part 6. What happens next? The departure phase and what to watch. October 29th, 2025 was Perihelion, the peak, the climax, the moment when 3I-ATLAS reached its closest approach to the Sun and burst into brightness. But the story doesn't end there. In many ways, it's only beginning, because what happens during the departure phase might be even more revealing than what happened on the way in. As 3I-ATLAS recedes into the darkness beyond our solar system, it will carry secrets that we might only catch if we're watching carefully with the right instruments at the right times. The observational window is limited and closing. As of early November 2025, 3I-ATLAS is moving away from the Sun at 60 kilometers per second, putting more distance between itself and Earth every day. The farther it gets, the dimmer it becomes. Following the inverse square law, brightness falls off proportional to the square of the distance. At some point, probably within 6 months to a year, it will fade below the detection threshold of all but the most powerful telescopes on Earth and in space. After that, it vanishes back into the cosmic dark and we'll never see it again. So the clock is ticking. Astronomers have a narrow window to collect data, and every observation matters. There are several key predictions they'll be monitoring, and deviations from any of these predictions would be significant. First, outgassing behaviour. As 3I-ATLAS moves away from solar heating, the rate of sublimation should decrease predictably. We should see the brightness fade, the coma contract, the jets and plumes weaken and eventually stop. This is standard comet behaviour during departure, the reverse of what happens on approach. If 3I-ATLAS follows this script, it supports the idea that despite all the anomalies, it's fundamentally still a comet, just a weird one. But what if it doesn't? What if the outgassing persists longer than expected, or flares unexpectedly, or shows activity patterns that don't correlate with solar distance? That would suggest internal heat sources, radioactive decay, perhaps, or stored energy being released, or chemical reactions occurring beneath the surface independent of solar heating. Second, structural changes. The radiation crust that we've talked so much about, that 50 to 65-foot shell of processed material, is under stress. Solar heating caused thermal expansion, outgassing created internal pressure, and the object might have experienced quakes or fractures as it passed through perihelion. During the departure phase, we might see chunks of the crust break away, exposing fresher interior material. If that happens, spectroscopy will detect it. We'll see changes in the emission lines, new molecules appearing, different ratios of volatiles. This would be incredibly valuable because it would finally give us a glimpse beneath the mask. Third, and this is crucial, non-gravitational acceleration. When comets outgas, the jets of vapor act like tiny rocket engines, producing thrust that slightly alters the object's trajectory. For 3I-ATLAS, we should see similar effects if it's truly outgassing. The question is, will those deviations match what we predict based on observed outgassing? Or will there be discrepancies, extra accelerations, or directions of thrust that don't align with visible jets? If there are unexplained trajectory changes, that's a red flag. It could mean hidden jets on the night side, or it could mean something else. Internal shifting mass, active systems, propulsion. There's also a call for something broader, data transparency across all observing platforms. NASA's JWST collected data on 3I-ATLAS. So did ground-based telescopes in Chile, Hawaii, the Canary Islands, and elsewhere. Radio telescopes have been listening. Space-based observatories have been tracking. All of that data needs to be compiled, cross-checked, and made available. Avi Loeb has been particularly vocal about this, arguing that transparency isn't just good practice, it's essential for resolving the controversies around 3I-ATLAS. Science works best when it's open, when competing teams can analyse the same data and check each other's conclusions. For those who want to follow along, the best wavelengths for observing 3I-ATLAS during departure are infrared and ultraviolet. Infrared captures the thermal emission from the nucleus and the signatures of warm gases like water vapour and carbon dioxide. Ultraviolet picks up hydroxyl radicals, fragments of water molecules broken apart by solar radiation, and can detect subtle changes in water production rates. Visible light observations are still useful for tracking brightness and morphology. Radio observations can detect certain molecules like carbon monoxide that are hard to see in other wavelengths. The challenges are significant. 3I-ATLAS is moving farther from the Sun, which means it's also getting smaller in angular size and dimmer. There are no space missions en route to intercept 3I-ATLAS. It's moving too fast, it was discovered too late, and launching a spacecraft to catch it would require delta-V budgets we can't currently achieve. So we're stuck with remote observation, which means we're limited by photons, light that travels from the object to our detectors. Let me walk you through two scenarios for how this could play out. Case A, normal departure. Over the next 3 to 6 months, 3I-ATLAS fades according to predictable curves. Outgassing diminishes as expected. The trajectory matches gravitational predictions with small, explainable non-gravitational corrections. Spectroscopy shows the composition stabilizing or changing gradually as surface layers sublimate away. By mid-2026, the object has faded to invisibility, and the scientific community publishes papers concluding that 3I-ATLAS was a large, unusual, but ultimately natural interstellar comet with properties shaped by extreme radiation weathering during its journey. Case B, continued anomalies. The brightness doesn't fade as expected. Maybe it maintains a higher level of activity or flares unexpectedly weeks after perihelion. Spectroscopy detects new emissions that weren't there before, suggesting the interior is very different from the surface. Trajectory analysis reveals non-gravitational accelerations that don't align with visible jets. Radio telescopes pick up periodic signals or unusual radio emissions that might indicate electrical activity. The more data we collect, the less it fits standard comet models, and the debate intensifies. Which scenario will we get? That's the question that makes the next few months so suspenseful. You could be witnessing a turning point in how we study interstellar visitors, not just this one object, but the framework for how we interpret anything that wanders into our solar system from the stars beyond. But while we wait for 3I-ATLAS to reveal its secrets, or take them into the dark, there are parallel stories unfolding that tie into this moment, developments in technology and research that change how we detect, study, and understand these cosmic visitors. Part 7, Parallel Story, Recent Breakthrough in AI-Driven Asteroid Detection. In 2025, while telescopes across the planet were tracking the bizarre behaviour of 3I-ATLAS, another revolution was quietly unfolding in the way we find and monitor objects in space. Artificial intelligence systems trained on decades of astronomical data began autonomously detecting near-Earth objects, flagging unusual activity, and alerting human astronomers to things that might otherwise have been missed. This isn't science fiction, this is happening right now, and it's changing the game for how we study everything from asteroids to comets to interstellar visitors. Traditional asteroid and comet detection involves automated telescopes that scan the sky, take images, and compare them to previous images to find things that moved. The moving objects are flagged, their positions recorded, and over multiple nights, their orbits are calculated. This process has been automated for decades, and it works well for finding known types of objects behaving in expected ways. But it struggles with anomalies, objects that brighten unexpectedly, or move in unusual paths, or exhibit behaviour outside the training set. Enter machine learning. Over the past several years, astronomers have been training AI systems on massive data sets, millions of observations of asteroids, comets, supernovae, variable stars, all the transient phenomena that change in the sky. The AI learns to recognise patterns, but more importantly, it learns to recognise when something doesn't fit the patterns. It becomes an anomaly detector, capable of saying, "I don't know what this is, but it's weird, and a human should look at it." In 2025, one of these systems flagged a near-Earth object exhibiting comet-like activity earlier than any human had noticed. The AI spotted subtle changes in brightness and the beginning of a coma formation before the object was officially classified as active. This early warning gave observatories time to point their instruments, collect data from the onset of activity, and track the evolution in real time. Now, apply this to interstellar objects. The challenge with objects like Oumuamua, 2I Borisov, and 3I-ATLAS is that they move fast and they're often discovered when they're already relatively close to the Sun. Oumuamua was discovered after Perihelion when it was already leaving. By the time astronomers realised what they had, the object was fading and the opportunity to study it in detail had passed. AI systems could change that equation. If machine learning algorithms are continuously scanning survey data for anomalous trajectories, unusual velocities, or objects coming from directions that don't match known solar system populations, they could flag potential interstellar visitors months or even years earlier. That extra lead time is precious. There's another advantage. AI can monitor multiple objects simultaneously and detect behavioural changes that human astronomers might miss. Imagine 3I-ATLAS's rapid brightening before perihelion. A human looking at brightness data once a week might notice the trend but not catch the precise timing. An AI monitoring in near real time could detect the outburst within hours, trigger automatic alerts, and mobilise telescopes while the event is still unfolding. For transient phenomena, flares, jets, break-up events, that kind of rapid response is critical. This ties directly into the 3I-ATLAS story because if such systems had been fully operational and monitoring the object earlier, we might have caught the onset of its anomalous behaviour with better temporal resolution. We might have spectroscopy from before the brightening started, giving us a baseline to compare against. But there's a speculative angle here that's even more interesting. Could AI spot probe-like behaviour in future interstellar objects? Imagine a machine learning system trained not just on natural objects but on theoretical signatures of artificial ones. You'd feed it data on how spacecraft behave, non-gravitational accelerations that don't correlate with thermal emissions, trajectory adjustments that look like course corrections, periodic signals that might indicate transmitters or rotating structures. The AI learns what artificial might look like, statistically speaking, and then watches for those signatures in the data stream. This isn't pure fantasy. SETI researchers have been using machine learning for years to search radio telescope data for anomalous signals that might indicate intelligence. The same principles apply to optical and infrared observations of small bodies. You're looking for patterns that don't fit natural processes, geometry, periodicity, correlation structures that suggest design rather than randomness. Of course, this raises concerns and controversies. One major issue is algorithm bias. Machine learning systems are only as good as their training data, And if that data is biased towards certain types of objects or behaviours, the AI will miss things outside its experience. There's a real risk of false positives. The AI flags something as anomalous, resources get mobilised, and it turns out to be mundane. Every false alarm erodes trust in the system and wastes valuable observing time. There's also the problem of black swan events, truly novel phenomena that don't fit any category the AI has seen before. Machine learning excels at interpolation, finding patterns within the space of known examples. It's much worse at extrapolation, recognising something genuinely new. That's why human oversight remains essential. AI should be a tool that amplifies human capability, not replaces it. There's a historical parallel worth mentioning. Asteroid detection evolved from manual plate comparison, astronomers literally blinking back and forth between photographic plates to spot moving objects, to automated digital surveys that process terabytes of data per night. That automation didn't eliminate human astronomers, it freed them from tedious work and let them focus on science. AI is the next step in that evolution. 3I-ATLAS arrived at a unique moment, when our technology is sophisticated enough to study it in detail, but not yet sophisticated enough to have caught it earlier or tracked it more completely. The next interstellar visitor might arrive when AI systems are fully operational, when automated alerts trigger coordinated global responses, when machine learning models trained on 3I-ATLAS and its predecessors can say, "This looks like that, prepare for anomalies." The broader implication is that 3I-ATLAS is not just interesting astronomically, it's part of a new era of celestial object monitoring where technology is finally catching up to cosmic surprises. Part 8. Parallel Story. New findings on cosmic rays and deep space, weathering of small bodies. While 3I-ATLAS was brightening and puzzling astronomers in October 2025, laboratories on Earth were publishing research that, almost coincidentally, provided crucial context for understanding what they were seeing. The topic was cosmic ray bombardment and radiation weathering of small bodies in deep space, exactly the processes that would create that 50 to 65-foot crust we've been discussing. Here's what the research showed. Cosmic rays and deep space radiation alter small bodies far more significantly than previous models predicted. Scientists have known for decades that radiation weathering occurs. It's been observed on asteroids, measured in meteorites, simulated in laboratories. But the new studies, combining updated cosmic ray flux measurements with advanced computer simulations and lab experiments on ice and mineral samples, revealed that the effects are deeper, faster, and more chemically complex than anyone realized. Outside the Sun's protective heliosphere, space is pervaded by galactic cosmic rays, mostly protons, but also heavier atomic nuclei like helium, carbon, oxygen, iron, all accelerated to incredible energies by supernova shocks and other violent processes. When these particles hit a solid object, they don't just bounce off. They penetrate, sometimes meters deep, smashing into atoms and molecules along the way. Each collision transfers energy, breaking chemical bonds, knocking atoms out of their positions, creating defects and new chemical species. A high-energy proton ploughing through water ice can break H2O into hydrogen and oxygen radicals, which then recombine in different ways, forming hydrogen peroxide or molecular hydrogen or hydroxyl groups. Carbon-bearing molecules get fragmented and rearranged. Over time, millions or billions of years, this bombardment creates a processed layer, a crust where the chemistry and structure are fundamentally different from the original material. The 2025 research showed that for typical interstellar conditions, an object the size of 3I-ATLAS would develop a radiation-processed layer 15 to 20 meters thick over a timescale of 1 to 2 billion years. That matches almost perfectly the crust thickness inferred from observations of 3I-ATLAS. This isn't just theoretical. Laboratory experiments have exposed ice samples and meteorite fragments to beams of high-energy protons and heavy ions, simulating cosmic ray exposure. The results show dramatic changes. Ice darkens, becoming less reflective. Organic molecules form from simpler precursors. Volatile ices get converted to more refractory forms that require higher temperatures to sublimate. These lab results validate the computer models and provide benchmarks for interpreting observations. The tie-in to 3I-ATLAS is direct and strong. The object's unusual surface behavior, the delayed dust release, the strange spectroscopic signatures, the blue glow from molecules like C2 and NH2 all become easier to understand if the surface is heavily radiation processed. Those molecules might not have been present when the object formed. They might be products of billions of years of cosmic ray chemistry, synthesized in the crust during the interstellar journey. There are other examples that support this picture. Meteorites recovered on Earth often show cosmic ray exposure ages, timestamps of how long they were exposed to space radiation before falling. Some have exposure ages of tens of millions of years, and they show clear signs of surface alteration. Japan's Hayabusa 2 mission returned samples from the asteroid Ryugu that showed radiation damage and chemical alteration. The principle is the same. Deep space is not a benign environment. It's corrosive, transformative, and given enough time, it can completely remake the surface of a small body. Why does this matter beyond just explaining 3I-ATLAS? Because it forces us to rethink our assumptions about what constitutes pristine material. When we study asteroids, meteorites, or comets, we often describe them as primitive, as samples of the early solar system. But if radiation weathering is as significant as the new research suggests, then even objects in our own solar system might have altered surfaces that don't faithfully represent their interiors. And for interstellar objects, which spend vastly longer in deep space, the surface might be almost entirely a product of the journey rather than the origin. This has practical implications for sample return missions and future ESO studies. If you want to understand where an interstellar object came from, you can't just analyse the surface. You have to drill down, dig through the crust, get to the interior material that's been shielded from radiation. That's technologically challenging, but it might be the only way to get reliable data. There's a speculative angle here too. What if some interstellar objects have surfaces that are so heavily altered that only a tiny core remains untouched? What if the radiation crust is so thick and so transformed that it functions almost like packaging, protecting something inside? For a natural comet, that something would be primordial ice and rock. For an artificial probe, it could be instruments, data storage, even biological payloads designed to survive the journey. I'm not saying that's what 3I-ATLAS is. I'm saying that the physics of deep space weathering creates conditions where such scenarios become physically plausible. The implications for interpreting interstellar objects are profound. Every measurement we make is sampling the surface or near-surface material. If that material has been processed for billions of years, then we're not seeing the object as it was, we're seeing the object as it became. To get at the origin story, we need to think creatively. Maybe we look for objects that are breaking apart, exposing their interiors. Maybe we design missions that can rendezvous with interstellar visitors and drill into them. 3I-ATLAS may turn out to be a textbook case of deep space weathering playing out in real time. As it recedes from the sun, as its crust continues to crack and shed under thermal stress, we might finally get glimpses of the interior. Either outcome teaches us something, either outcome refines our models and prepares us for the next interstellar visitor, and there will be a next one. The galaxy is full of wandering objects, and our detection capabilities are improving.